The night sky glows with questions, stars, planets, nebulae, just shiny blobs to our eye. But every light holds a secret. I'm Vijay, this is Stellar Relay. Let's uncover what's out there.
Out here in the vast unknown, where rockets rise and black holes groan, we chase the light, we chase the sound of stars and dust spinning all around. From Martian dreams to Saturn's rings, from shiny blobs to future things. Every fact, each flare, each cosmic play, you'll find it here on Stellar Relay.
They are everywhere in the night sky. Those tiny points of light we often take for granted, but each one is a massive blazing sphere of energy, millions, even billions of times larger than our planet. We call them stars. They light up the universe, shape galaxies, and make life possible. In this first episode of Shiny Blobs, we are diving into the most fundamental blocks of the cosmos. And we're gonna see what stars really are, how they work, and why they matter. Let's dive right in. What is a star? At its most fundamental level, a star is a luminous spheroid made of plasma held together by its own gravity. But let's unpack that a little bit further. Imagine a colossal incandescent sphere, not made of solid rocks or liquid, but plasma, a fourth state of matter where atoms are stripped of their electrons due to extreme heat, creating a superheated ionized gas that isn't just hot air, but it's a dynamic, electrically charged soup of particles. Think of it as a giant superheated ball predominantly composed of the two lightest and most abundant elements in the universe, hydrogen and helium, which are also the first two elements of the periodic table. And what makes this particular shiny blob so special and utterly vital? The key distinguishing feature of a star is that it doesn't just glow from residual heat, it's an active powerhouse. It generates its own immense energy through a process called nuclear fusion deep within its core. This is where the magic truly happens. Under unimaginable pressures and temperatures, lighter atomic nuclei like hydrogen are forcibly combined or fused to create heavier nuclei like helium. This incredible process unleashes a staggering amount of energy, which is then radiated outwards, fueling the star's brightness and warmth across vast cosmic distances. Some key characteristics of stars, including its composition, which was made up of hydrogen and helium, hydrogen being 70% and helium being around 28%, with trace amounts of heavier elements, which are often called metals by astronomers. And also, we've seen the energy source, which was nuclear fusion, which we will soon discuss in a detailed explainer episode. And also, now we're coming to a star's delicate balance, which is between the immense inward pull of its own gravity, which is perfectly countered by the outward pressure generated by the nuclear fusion at its core. This balance is called hydrostatic equilibrium. This is what keeps the star stable for billions of years during its main sequence phase, which we'll discuss in a little while. Next, let's talk about the temperature and color of a star. These are two important and related parameters because the surface temperature of a star determines the color of it. And these temperatures range from 3000 Kelvin to 30,000 Kelvin, and their colors can be easily understood through the Hertzsprung-Russell diagram. It also mentions about the types of stars, which we'll see about in just a while. So, hotter stars are bright blue or blue-white in color, which include the O and B type stars, and intermediate temperature stars like our Sun or G type stars appear to be yellow or yellow-white. On the other hand, the cooler stars like K or M type stars are orangish or reddish in color. Much like all the other parameters, the mass is the most crucial property of a star. It dictates almost everything else about its life: its luminosity, its radius, and even its lifespan. More massive stars are generally much more luminous, which means emit more total energy than less massive stars. More massive stars are typically larger. Ironically, more massive stars burn through their fuel much faster and have shorter lifespans than less massive stars, which means they live fast and die young. We've mentioned luminosity and apparent brightness throughout this episode, but these are two very different things. Luminosity is the total amount of energy a star emits per second. It's an intrinsic property. Apparent brightness, however, is how bright a star appears from Earth. This depends on both its luminosity and its distance from us. A very luminous star far away might appear fainter than a less luminous star which is very close. Now that we've understood the various parameters which discuss about the star's size, color, brightness, etc., let's see how the stars actually form. Stars are born from vast clouds of gas and dust called nebulae. Disturbances can cause denser regions within a nebula to begin collapsing under their own gravity. These disturbances can be due to supernovae or stellar winds, both of which we'll soon uncover in a later episode. As the gas and the dust fall inward, the core of the collapsing cloud heats up and becomes denser, forming a protostar. It glows from the heat of gravitational compression. But when the core of the protostar reaches a critical temperature and pressure, which is about millions of degrees Celsius, nuclear fusion ignites, the same nuclear fusion that we talked about some time ago. This outward pressure balances the inward pull of gravity and a new star is formed. This was the hydrostatic equilibrium, which we also talked about a while ago. Now let's talk about star classification, which we missed earlier. Astronomers sort stars into types based on how hot they are and what they are made up of. The system uses a sequence of letters, which are O, B, A, F, G, K, and M. These are ranging from hottest to coldest. Now here's a quick breakdown. O-type stars, which are the hottest and most massive, shine bright blue and burn through their fuel very quickly. Meanwhile, B and A-type stars are still very hot and luminous but glow blue-white to white. F-type stars are slightly cooler with a white to yellow-white glow. And G-type stars like our Sun have a medium temperature and mass glowing yellow. K-type stars, however, are cooler and smaller. They appear orange. And M-type stars, the most coolest and most common type of stars, these small, long-lived stars glow red and can burn for trillions of years. We've seen a lot of things about stars, but before we end, let's see a little about the life cycle of a star in general. While the specific end of life stages may vary depending on the initial mass of a star, all stars follow a general path. First, their birthplace, which is the nebula, then they become the protostar, which we talked about earlier, and then they become the main sequence star, which is the longest, most stable phase, like our Sun. And this is where hydrogen fuses into helium, which we also talked about earlier. Now, post main sequence, once the hydrogen fuel in the core depletes, the star leaves the main sequence phase. Now, if it was a low to medium mass star like our Sun, They become red giants, then shed their outer layers to form planetary nebulae, leaving behind a white dwarf. If the star was massive enough, it would become red supergiants, then explode dramatically in a supernova, leaving behind either a neutron star or, if the star was massive enough, a black hole. All of which we'll see in detail in future episodes. So there you have it. From the swirling cosmic dust of a nebula through billions of years of fiery fusion to their final, often dramatic, explosive finales. These shiny blobs, these stars, are far more than just distant points of light. These are cosmic furnaces that forged every atom heavier than hydrogen or helium. The carbon in your body, the oxygen that you breathe, the iron in your blood, all of it was once forged in the heart of a star billions of years ago. You are literally stardust. They are the lighthouses of the universe, illuminating the vast darknesses and providing fundamental conditions for planets and indeed life to emerge. When you gaze up at the night sky, you're not just seeing stars, you're witnessing the fundamental building blocks of everything, the cosmic architects painting the universe with light, one incredible shiny blob at a time. So the next time you look up at the night sky, remember those shiny blobs are more than just pretty dots. These are nuclear engines, storytellers of time, and the very forges of creation. This has been Stellar Relay with Vijay, and we've only just begun. See you next time as we continue exploring the cosmos. Over and out.